Cool, cool.
Oh, Rishi,
Hi.
you were saying.
Oh, that's the wrong guy.
Hi. It's
Did
me.
you see my message in Discord?
No, I couldn't.
Okay, cool. Check it.
Oh, thank you, Dave. That will be good.
I just summarize, brief summarize, if you have more, then you continue. I think we reached here last time. Okay, I think you don't know. Okay, this one. Action. Action. Okay. Okay, that is what we reached to the end of last class. So today we keep continue, discuss this, and depending on time, we will Cindy can introduce about the constraint. So remember we discussed the many particle systems. We first introduced center of mass, right? Center of mass, this one. Then we discussed what is total linear momentum. We found that total linear momentum actually is nothing but the center of the linear momentum of center of mass. Then the dynamics of total linear momentum is nothing but the dynamics of the center of mass linear momentum equal to sum of all the net force on each particle. Then we sum together, so what we found, if the internal force follow the weak law of action reaction, this is third Newton law, then we found that actually the dynamics of total linear momentum is driven by only the external, right? External force. So that is the dynamics of this linear momentum. Then we go to the angular momentum. First, we calculate the total angular momentum to be sum of all this angular momentum around each side. Then what we found is a summation of two angular momentum. Angular momentum. So first one is angular momentum of center of mass, which is here this R is a center of mass, cross product of the linear momentum of center of mass. Second one is relative angular momentum is rotated about the center of mass with this R prime relative displacement, relative momentum. So when we obtain this, the next step is we are going to see the dynamics of total angular momentum, right? And before we do that, we analyze or we discuss so-called strong law of action reaction. That is, in addition to the weak law of action reaction, if the RIGS distance between two particles, right, parallel to the interaction force, then what we found this pair is equal to here because I have an next sign up by the weak law of interaction reaction. Then since this cross product is two parallel vector cross product is 0, right? So we have this. So with this, now we can discuss the dynamics of the total angular momentum. What is dynamics of this? Okay, so by relation we know that's the total angular momentum sum of all the individual, right? So we just, since we already studied the single particle, then we just sum of all this for single particle. Then for single particle, we have here. Okay. Just remind you, right? So single particle, we know this is net. Is each S particle has a net top, right? So that is equal to this sum over all the net top. Then the net top is equal to the net force. So we have this RI cross product of net force on each particle, right? Then since we introduce this internal force and external, we separate this one into two parts. So that is right in RI cross all this ice particle, external, right? When I say that external, maybe not only one, it's several. So several external force that is torque due to the external force plus the internal, right? So the internal part is I here, right? I from 1 to n. And then for each I we have a j, right? So sum over j not equal to I. Then this r I cross with ji, right? That is internal part. External, because this term includes two parts, right? External and internal. Then this one we apply. So if not, we cannot go to further, right? If this is weak and strong, these two laws apply, right? Laws apply to the system. Then we can immediately know this summation I from 1 to n, j not equal to I, all this cross product should be equal to 0 somehow, because here with this summation we can extend as a summation of a pair, right? So here this two summation together is summation of all the pairs. And each pair we are just add together, I, j, j, I, then we find the class equal to 0, right? Another pair is another 0, right? So that is all pairs. So we have this 0, then we can immediately get this total angular momentum. The dynamics total angular momentum, this disappears, so only contribution from the external. External net force, and then that is here, right? The top. Sum of all the net torque, but due to the external. I write this way, right? Since this one equal to this, right? Net force. So that means there's another summation implied, right? I didn't write down, but here when we say net means all the external force together with this, that is the net top, right? External force. And then this add together, if I give a name, that is total external torque. So if you look here, this is a linear momentum is total external force. And the dynamics of a total angular momentum controlled or driven by the total external torque, right? That is if we satisfy this big and strong laws. Then we have this story here. Then you can discuss something in details here. So be careful is here. Is this one. So this is the left-hand side, right? Now let me go to that is dynamics of center of mass angular momentum. Since the total angular momentum is here, right? So left-hand side is two terms. That is be careful. So what that means? The total external torque control the dynamics of center of the angular momentum of center of mass. Another is angular momentum, relative angular momentum about rotation about the center of mass. So we have two terms. Here, only one, right? Only center of mass. So that is different. And then we can discuss, suppose if this is 0, then only the relative rotation angular momentum is controlled by the external torque. In most cases, you select the rotation axis is located at center of mass, so this term disappears. Right? Okay, and we can also discuss the conservation if this total external torque is 0, then the system, the angular momentum is conserved, right? I think that is, if total so we look this total external torque 0, the total angular momentum is constant and is conserved, but not equal to the addition of 2. Not be careful here. Add together is conserved, right? So that is case, and since this vector, there are also this is a restricted conservation. If one of direction around the x direction, this external total torque is 0, so the total angular momentum project to the x direction is conserved. Others still not, right? So this discussion, I think you can just discuss yourself. Now we discuss the total work, kinetic energy, and potential energy, as well as the total energy. So, okay, 3. Okay, so this is the next job, and this is very important. As later you will see, we are going to transform from the Newtonian mechanics to the analytical mechanics. To the analytical mechanics, we are going to analyze this, or we are going to determine those energy, then we can apply this Lagrange equation to study the dynamics. Newtonian mechanics, we need to analyze the force, right? Here, force. Force, when the force has a force, we have a torque, then we need to study the dynamics. So that is different. So now we are going to learn how to determine the total energy, or kinetic energy, potential energy in the many-particle system. First, let's first the total work. We use capital W, total. Total work, the m particle of total work to be sum over all these, the work done on each particle, right? So here, summation from 1 to n. We still consider this path from 1 to 2, right? Among this path, how much work done on the system? We have n particle system. So the total work done on the n particle system is sum over all each individual. Let me just use I. Okay, I enough. And then each one is the work done on each particle, so we know from 1 to 2, that is total ice particle has a net force, right? And do the work along this displacement. That is this term, right? That is Wi. Then, okay, we are going to first apply for each single product, each single particles, the work done on particle. That is this formula we already discussed in this first part of a single particle. So I'm going to direct use that result to simplify. This one, if you agree, 1 to 2, let me, if I write down here, see whether you are agree. Remember this? Okay, I then send to another intermediate step. Since from 1 to 2, this one is the dynamics of Pi dt, right? This is a net force dr. and dpi dp is dmi dvi dt, right? And then we have an intermediate. Just go back to the single particle, you remember this. So this is nothing but this dTi, right? Kinetic energy. Then from 1 to 2, so that sum over all from the particle Ti at the position 2 minus Ti position 1. The change of kinetic energy of S particle. Then the total change sum over all the particles together, so that is, I'm going to use T2 minus T1. I use capital T means the total kinetic energy, so here, okay, let's use T2, T total, so that's T total, 2, T total, 1, and this figure. So now we have a T total is equal to sum over all the particle, n particle, each particle has its own kinetic energy, right? This notation here first, Ti. And then each Ti is half of Mi squared, right? So since we already have discussed this single particles, we immediately know how to obtain the total kinetic energy of n particle system. Okay, so that means if we have n particle, you first find this, and then you sum all together. Alternatively, that means we have another way to express total kinetic energy. And sometimes this way is easier, another way is also helps. So that depends on the system. So now, let's look this one. Total kinetic energy, by definition, right? Total. Let's see if we can rewrite the total kinetic energy in this way. Sum over all from 1 to n, right? So now here, this Vi squared is inner product Vi, right? So I'm going to rewrite here that is Mi half. Rewrite this one is Vi inner product Vi, right? Then we are going to use this relative velocity since we introduced center of mass. So now, so each one, Vi is with center of mass plus Vi prime, right? Remember? This Ri, so that is capital R, this Ri prime, right? Then if you do the dot, right? So that is this, okay. And inner product. So we look this inner product, we have 4 terms, right? One is the inner product between the center of mass velocity. Another is center mass multiplied V prime, or V prime center of mass. These 2 terms are same. And the last one is this Vi prime squared, right? So we have, now let me write down, and we see sum of terms 0. So half of, okay, this one, since VCM does not depend on I take outside, right? So I have a VCM squared sum over all. This term is Mi, which is nothing but the total mass. Second term is this one multiply this one and this one, so we have a 2, right? 2 multiply, we have a half summation I. Actually, I can take VCM outside, right? Inner product. This summation I from 1 to n Vi prime. Do you agree? Then the last term, right? Last term is this half of half of summation I from 1 to n Mi Vi prime squared. I don't need this factor since this is inner product. Only this term I have to introduce here because they are different, right? So how about this term? Remember this is equal to 0, right? We already discussed before. So now we have only the first term and last term. First term, I'm going to use kinetic energy of center mass. right? Because this is the mass. This is the total mass, right? Capital. Okay, maybe since this is the first time I read another intermediate step, so I'm going to use capital M, ACM squared. And the last one is half. Take the half in, half outside, inside is fine. Okay. M-I-E-I prime squared. Now equal the first one, since it's total mass. So that is we consider system as a total mass centered at the center of mass and move that, and with that kinetic energy, right? So that is kinetic energy of center of mass. Then the relative kinetic energy, I use T prime. So T prime is here, the relative kinetic energy. Right? Then you see here, as a single particle, the total work done on the system due to this the total net force is equal to the change of kinetic energy for single particle. For total many particle system, it is equal to okay, that is here, change of total kinetic energy. Then the total kinetic energy can be written in two ways: either just simply sum over all the single particle kinetic energy, or sum over two terms. One is the center mass kinetic energy, another is the relative kinetic energy. You may ask why we need these two. Let's see which one for different system. You will see you can select either the first one or second one. The reason is we want to try to find the kinetic energy, total kinetic energy is as easy as possible. Right? So now let's do the first one. Okay. Consider we have poly and this poly we have 2n we have 2 mass. This is m. This is m1 and 2 and 3. This is actually this is the kind of center here with an R here. So this is MC. Okay. How to write the total kinetic energy in this case? So I'm going to say the total is equal to, you can either write this way or this way. So let's consider if you write this way, you need first find where the center of mass. Is that easy for this case? Not easy, right? This is also change, right? So in this case, it is either just sum of all the individual. So, because if you try to, this is a fix here, just rotate, right? These two up and down. So you try to find the discuss or calculate the center of mass. Yes, you can do that way if you prefer. Then relative kinetic energy, you try to write relative to where the center of mass is also changed. You move, then you need to find. But this way I prefer use this. Since now, this one is simple, right? So, and this one, here, T3, I want to write down here. If it is, has a mass and rotation, so T3, I'm going to write down T3 center of mass of center and plus T3 prime. Because this, if you think this is a many particle form this disk, then that's a many particle system, right? So for this system, I know center mass is a center. So I can use this, and you know in this case 0 because this center fixed, right? Then only this one. This one you know this half of, only the square and the moment ignition, right? And if you know this, you know this, right? So this depends on different type of the system. How to, is a geometric parameter, right? How to determine that. So, moment. So you can see then now, let me further, since this is the first time I just write down the details. M1 squared, M2 V2 squared, and plus half of. I'm going to distinguish, this is only the rotational, I mean, M3, right? Okay, that's fine, since there's only one condition. So you need to find this. Now once you know this, and you define the coordinates, x1, x2, so then you know how to find x1 dot is v1, right? x2 dot is v2. So that is this system we are going to use. Now how about the second one? The second one is we have like a molecule, right? We have two M1, M2. Okay, so this motion is relative change or movement, along the line. So in this case, we are going to suppose this is center of mass here. And that is either R1, let's say just R1 prime, or X1 prime if one dimension R2 prime. So if I select this, I find that is simple since these two together also move, right? So we have, in this case, I prefer use the second formula, is the center of mass plus the relative kinetic energy instead of a 2. If you write the summation of 2 is also okay, but you need to find the coordinates such that you can calculate the absolute velocity. So in this case, if the center, I think that's enough. Depending on if the center of mass is does not change, this is 0, and only this one. And this one, okay, now this one is half of M1 V1 prime squared, right? Plus half M2 V2 prime squared. So you set your coordinates already here, then you can define what is x1 or r1 and r2 prime, r1 prime, r2 prime do the dot because v1 prime, v2 prime. So in this case, I prefer use this. The third example is we have this disk rolling down on this. Okay, so we have the rotation here, and this is the center of mass. Center of mass has a velocity rolling down, right? And you consider this as many particle system, and all the particles relative to center of mass make the rotation. So immediately you know this one, I'm going to use the second. It's easier. Since center mass in this case is very simple. It's just a linear translation, right? And then this one is rotation. If you have now this angular momentum, you just add that. So you can see, really depends on how this the many particle system, the mass distributed. Then you can either select this one or this one. Okay, we have a kinetic energy. Now we introduce the potential energy. After that, we can have the total energy, right? So the potential energy we know that's come from the conserved force. So now let's analyze the force. So the force, okay, each individual particle, the net force is external. Net, I always use net, be careful. Here, it's not only one of the external, and plus internal, G naught equal to I and 3I, right? And here, so for this one, external net, we can decouple into conserved force, external net. Again, I'm going to use net, conservative, plus the remaining are external force on the ice particle, which is net non-conservative. So I'm going to separate this. And we know for this one, since it's a conserved force, we already described the single particle, that means there exists the field potential energy. And the force is negative gradient of that, right? So very easily, I think that the details we already put in single particle. So here, this one, this is net. Then I'm going to write down in each individual. Net means there are several, right? So for this, for those conservative external force, always equal to negative gradient. Now here, since ice particles are happening at time. If only single particle, you just do the gradient of potential. So now since we have ice particle, each particle has its own potential energy. So the gradient with respect to this particle, right? And this index I, V I, but this potential is external. Now this potential is associated external force. It's not internal force, right? So we are going to distinguish this. Okay. Once we have this, then you can immediately know this the work done because this, right? So the work done from 1 to 2, the ice external force, conserved force, do the work on the ice particle from 1 to 2 is ice particle conserved. I didn't use net right here. This net is some of all the conserved force. Just some one of them. Conservative, external, do the work, drag the ice particle around 1 to 2 to the displacement dri. That we already discussed in this the single particle energy, associated with conserved force. So that is I, external, and that gives us difference. Is negative of V external, the ice particle from 2 minus external ice particle to 1, right? Just difference because we know this work done on the conserved force does not depend on path, just depend on initial and final position. So that is this one of this conserved force, external conserved force. Now we are going to add all together, right? So all the work done by this external conserved force is sum over all from 1 to 2, and this external ice particle net conservative DRI. This one is one of them. So now I add all together, and you will see that's be the same. So that's be negative sign. We have all the negative signs sum from n to the I from 1 to n. Then let's do the integral from 1 to 2, gradient of ice. Here, I write down net. Again, that means is another small summation. I just want to make it simple, so I just say net. Then that is finally is summation I from 1 to n. External potential energy of the position 2 minus external potential energy of position 1 as particle. So that is the total work done by this total net external conserved force. Okay, let's put here then we are going to write down the total potential. Now that is the first look this track, right? Now, for this one, we just analyze this conserved. Now we consider this the internal the total is equation Gi is equal to Fgi conservative plus, usually we know the internal all are conservative, right? Just consider in general if there is non-conservative. So now let's move this one. We leave the non-conservative in the last. So now we know this is a conservative force with associated with this gradient. So now let's do this. Consider one of them, right? Gi is conservative. To be associated with negative gradient I's particle potentials Ij function of Ij. Here, this potential is internal potential is the interaction between two particles generated by this internal potential, right? So I use index Ij. Distinguish this external. Like if you consider like a molecule, right? Molecule, you know the external is gravitational potential. If the molecule is charged, particle maybe has the cooling potential, but the internal is the interaction between the two molecules, right? So that is this index. So now, before we go down, we are going to rewrite this one in terms of this gradient with respect to Rij, not with Ri. This is with Ri, right? So you will see this difference. Okay. Now, in order to do that, let's consider one of the components. Then, if we know one of the components, x components, and then you will see how to get the total, right? Because it's y components and this unit Ji, right? And J components, Z components is 3. So now let's look at this one. F Gi x components. Okay. But this one is negative. Gradient is partial Vij, partial Xi, right? The gradient, you know the gradient, right? Gradient is partial the function with x components, partial y, right? So I need to write down to remind you of this, what is gradient. Partial x, I, just say in general. Partial y, j, partial z, k, right? That is a gradient. So if the function is Vij, so this means partial Vij, partial xi, partial Vij, partial yi, partial Vij, partial zi, right? So I just select this one is this x component. So now this is xi. I want to do mathematically we know this we can use so-called chain partial derivative like this partial Vij into the partial Rij, which is magnitude of Rij. And then I need to multiply partial Rij, right? And partial xi. Do you agree? I divided it and plus. So these techniques we always need to use, since that can help us to analyze, make this term is more classified into several groups. So I'm going to keep this one, let's do this one. Rij is magnitude of x I minus xj squared plus y I minus yj squared plus z I minus yj squared, right? So the partial Rij, partial x I is equal to, first takes half, right, square root, and then denominator I will, to save time, you just write down this here, right? And then half, and then here, 2 multiply. So this is partial x, right? 1. Yeah, sorry. that is square, so that is 2xy minus ij, right? And 1. So ij, that is, right? So this is r, right? So then 2 to cancel, so that is rij xi minus ij. That is this. So now I put here minus partial vij, partial rij, partial x, y, sorry, not partial. This is another thing. So x, y minus j, rij. Okay. I think you already got some idea. If I put the y component, z component together, so I will not do that. You do the same thing. Therefore, now we can come to here. The i's ij, the conservative. This force is negative. I Vij, right? So now it's negative. Since it is equal to the three components, right? The first one is partial Vij, partial Rij, xi minus xj, Rij, I hat, right? And then partial Vij, partial Rij, and yj minus yi minus yj, Rij, j hat. And the k, I mean, z components, I just demonstrate. So that is negative. What is that? This is partial v and j, partial r and j. And here, this is vector, right? So that is vector of r and j, right? Because this is the x component, the difference xi minus ij is rij x components. This is Rij y components, right? So that is Rij, this, and this one is what? Unit vector along the Rij direction, right? So this one. Then I'm going to write, so then that means what this one? Now is Ij. Let me see to give a notation. Yes, okay. Ij, Ij. Yes, okay. So from here to here, because this is a vector, right? This gradient. And this gradient is vectors along the Rij direction. That is controlled by this. So this combined together is this one, right? It makes sense? Okay. So now you say why you do this way? I just want to convert what is here. Gradient is Ri, but I change this one. Then we can do, you see, apply strong law of action direction to cancel each other. Okay, so that is the first step. We try to rewrite this both. And with this one now, next we are going to analyze the action direction, which is, so, okay, now. So if the system, right, if system obey, system, a single system, the system obeys the weak and strong both. If not, we cannot discuss this cross product. So all this, yeah, we will need this one, strong laws of action. Okay, then we know since this Fgi is equal to negative Fij, that is weak. That means the gradient of Ij Vij is equal to negative gradient of Gi Vgi, right? From here, since this we already obtained this Fij or Fgi is this one, so we can have this relation. The only difference you can see that orders different, I, J, J, I. The general is not equal, but now if we apply the this here, to use this example again. You have this formula here, right? So I will use that one. So now, that that is a weak law. And then, if then we are going to use Rij parallel to Fgi. The second strong law of this action reaction. That gives us what? If this the interaction between the or the force between the two particles is along the line between the two particles Rij, then we will have the gradient. Okay, the gradient, because the force is proportional to this gradient, right? This is also or can be expressed in general is function of Rij. It can be, it's because along Rij, right? So that means along, let's just direct those Rij, and another is a scalar function. We do not know, but whatever scalar function which only depends on the magnitude. Do you agree? So that means if we satisfy this strong law of action reaction, this gradient or this force actually directions along controlled by the Rij because they're parallel, and multiply the potential energy, which is a scalar function. I mean, it is not potential, it is gradient of potential energy. Is this term? This part, right? So, but at least we know independent of this Rij because it's magnitude. Therefore, then we have this one give a conclusion first. The potential energy only depend on this the position magnitude. Does not depend on the orientation. And second, so Vij Rij is equal to Vgi. But I and G are the same, right? Since only depend on this magnitude. If the distance same, the potential energy on the I side and on J side be same. That makes sense? Okay. So with this, now we can go further. We are going to apply this together to find this. What is it here? So now let's look this. Look the pair because the force, the internal force, conserved force, do the work on the i's or j particle along the path from 1 to 2 is we got the summation I and j, I from 1 to n, j from now equal to I, right? We just select the pair. The pair is the j's particle exert force on the i's particle, conservative, do the work on the i's particle, plus another pair is the force of j's particle exert force on the i's particle, and that is conservative, also conservative force. We do not and move the particle, j's particle, is infinitesimal displacement drj. Let's look at these two terms. So these two terms are together, since we know the summation can be a summation of all pairs. Right? Now we are going to use this. So the first one is a negative. And let me just, since we from initial is this one, right? Is reading with the i's part position, potential Vij, and I will. I already write down here, right? So I just function of Rij, just about that. That is this one, and dri minus this one is gradient of j, Vij. Now I, j, j, I is the same, right? Already used here. Gradient of drj, right? So then, since here is negative gradient of Rij, Vij, dri minus gradient of gi, since I, j, j, I, the potential is the same, so just gradient but not same, the opposite, right? So then we are going to apply this weak law and just erase, right? Since this one just equal to opposite direction, here keep first still negative delta Ig, Vig, Dri. And now the second one, delta Ig is be negative of here, Gi, right? So negative become plus. Then the index is the same. So now this index is the same, right? Here this Gi, so I change this paper the right side. Vig dot Drg. Okay, now since these are same, I take outside, right? So I take negative delta Ig, Vig outside. The inside is Dri minus Drg. This one is Drg, right? Okay, so now this inner product here. Now we have this pair. So with this pair we know, now finally we are going to look this old work done by this external force, conservative external force. On the O particle we have some more O. This integral from 1 to 2, the internal Ig conservative Dri, right? That is the old force. Do internal force, do the conservative internal force, do the work. So then we can say some more old pair. Now I'm going to have a half. Since if I divide the pair, so each pair is 2 terms, right? So I have divided half. And from 1 to from 1 to n, and j from not equal to I. And inside we have 2 terms. Okay. 2 terms, right? Since this one, right? I, J, G, I are together, so that they'll have a half. So that is F, I, J. Conservative Dri plus F, J, I conservative Drg. That is nothing but this term, right? So this is this term, and this one is all pairs. Then we have, I already reached down here, right? So then, here. So finally, it is negative. I just use this negative sign, come here. Negative half is here, right? Summation still keep here. Okay, from 1 to 2 is this one, right? Delta Ig, Vig, inner product Drg. So now it's Drg. And this one is Drg, right? Total difference, change of this potential. So now finally we have a negative half of summation I from 1 to n, and summation j not equal to I, Vig at the second position minus Vig first position. Because this one is total difference of Vig from 1 to 2. Right, so that is this. Okay, now we can summarize. So you see we have 2 parts. One is from the external potential, another is internal, right? So this one is internal. So now I have a total potential energy we are going to, right? If we have a system, we are going to analyze what is the total potential energy of the system, many part of the system. So that should be plus is a total external potential energy plus the internal, right? So internal, I just write down this because we cannot use one symbol here. Vig. And this one, I will erase here. This one is summation. For each ice particle, we have a 9 external. So that is this term. Okay, be careful here. The total external potential is, for each side we have a total external potential, but not if you have several, not only one external potential, you have to add together. This is internal, right? So now we have two. Then let's go back to here. We see how can we obtain the total internal potential for this three case. We have already have this how to obtain the kinetic energy in this way. So now that's this one. Okay, in this case, total potential is equal to the external here, right? Sum over all the part. Also, we have three, right? So V1 external dot over C1 In this case, only one, but in general, careful. External V3 and last internal. Internal, we have V12 plus V13 plus V3 Since it's a half, right? The half I not equal to j, so we have that is for I we have 1, 2, 1, 3. Then for I equal to 1 and I equal to 2, we have a 2, 3, 2, 2, 1. So they duplicate, right? Then we have a half. So that is potential. Now here, this 3. In this case, okay, I'm going to write again. So in this case, what is the external potential? Only gravity, right? They just match. So if I select, let's see, select this as 0 potential reference, right? For gravity, because potential is always relative to some reference. If I select the center of mass of M3 is 0, so this term 0, right? And only this term. So we have V1, and now I remove 9 because only 1, right? V1 external plus V2 external. And this 3, okay, let me rewrite again. This 3 is what? Is interaction gravitational attractive between M1, M2, or M1, M3, or M2, M3, right? That is something like G or minus M1 or Mi, Mj, Rij, right? This type. This one also gravitational potential energy from the Earth. This is a relative between the particles. So compared with those, this is a very weak, right? Very small. So in generally, just ignore. We can ignore. Since it's very small. Then finally, in this case, this is enough. Just 2 mass has its gravitational potential. So just that's why when you write down the system, the potential is only have these two terms because according to the formula, we analyze which term equal to 0 if we select this center, the 0 potential level is the center of mass of M3, then M3 is 0. Then the other internal potential energy compared with external is very weak, so we can ignore. Any question? Does that make sense? Okay, good. Then we go to this one. So this one, kinetic energy we already analyzed. How about the potential energy? In this case, we consider this like screen. So in this case, I think, let me rewrite it. Okay, because like a molecule, two atomic molecule, the relative vibration with respect to their center of mass. But we know this is the initial at equilibrium, we have a distance, right? Either compressed or extend. So this, the potential is this hook potential, right? Or spring. So we have this is xx, that is the relative displacement with respect to the initial equilibrium distance, right? So that is this case. Then the potential, total potential energy should be, in this case, we have external V1, external plus V2, external. In general, I have to write down 9, but we know this only one. And potential is internal potential, which is just yeah, okay. I'm just add from 1 to 2, G nothing to I, right? In general. So now let's look this 2. Suppose we consider this diatomic molecule placed horizontally. We just consider if this is horizontal, right? Horizontally. So then we select the 0 potential level along the line. There's only gravitational potential, right? If we consider, if this is a charged particle, you will consider the Coulomb, but we just consider Coulomb potential actually just interaction. So now, if external is only gravitational potential, and then we select this along the line as a 0 potential, so these two are 0, right? Then only this one. And this one is this Hooke's potential. The first one is half of, if we have this the spin, the elastic constant K, then we have the relative displacement of this m1 with respect to the equilibrium distance is x1 plus x2. That is come from this term, right? Okay. Third one, let's look at this. How to write the total potential energy of this system. When total is V external. Now in this case, let's just be external. Only center of mass, right? Since you can also let me write the intermediate step. And some or if considered all the particles formed this, then you can consider this many particle system. V I external and in general is 9 and plus the internal. So this one is some of all the you see each one, if I select this as a 0 potential, then each one has the height, right, mgh. So you mghi. So you sum all together, actually, this one is equivalent to the center of mass potential. If I use the center of mass is the external, right? Center of mass. Okay, and plus this one. This one should be constant. Since the interaction between the S particle and G's particle, if this is I, if this is G, distance doesn't change. This is like a rigid orbit, a body, right? So the interaction will not change. Whatever you rotate or down, go to, this is constant. I keep here. We do not know, that's very complicated, since it's a many particle system. So the potential of this one, if you want to write down external, because this is already external, so that is M, capital M. If we have this, we can use the lower M, mgh plus constant. That is how to write the total potential of this. And h is center of mass. Yeah, this is h, right? And how to calculate h is mathematically, you can determine where you are as a reference, and you take. All right, so that is the kinetic energy, how to determine total kinetic energy, how to determine the total potential energy. Then the total energy is sum of these two, right? So that is very simple. Total energy. E total is total kinetic energy plus total potential energy. And then if you write okay, I think each one already have the formulas, I will not write that. And then now, the total work done is equal to the total change of total kinetic energy, right? This is the first step we discussed. It's the left hand side. On the right hand side, we have a negative total potential energy, 2 minus total potential energy, 1. That is from the conservative force. And plus all the non-conservative. Here, we couldn't get any expression, general expression for this. So we just put all together, non-conservative force do the work. So that is this. Then we move this to get to the left hand side, so you will see there's a total energy difference or change is equal to how much work done by the non-conservative force. And this, I think you're familiar with, is work energy theory, right? If there's no non-conservative force, it's conserved. All right, so now so far we have covered all this, the single particle and many particle dynamics. Now we are going to begin to try to derive this Lagrange equation. Before they derive that, you will see there's one particular force. It's very complicated, and because of that, so people try to consider or develop the analytical mechanics or dynamics. So constraint. What is constraint? Okay. Let's consider we have the object x, y, and z. This object can move along x, y, and z, right? Free. So this is the motion is free in 3 directions. Right? How about this? If we have a curvature surface, then now we have an object move here along this direction. This is a surface. So what happened? Since the surface holds this object, the object cannot come down, right? Always move along the curvature of the surface. That means it restricts its motion only along the surface. So this one, we call the motion is limited. In this case, the motion is limited along the surface, on the surface, right? Curved surface. So this limitation we call the constraint. So that we introduce the constraint. What is constraint? What is constraint? The limitation on the motion. So if we find the object motion, there's a limitation, and with some condition, that means there is a constraint. That is to be considered. We are focused on this. Okay. So if this constraint Then the motion of constraint, so we can say constraint motion is the motion under the constraint, right? Under. Now, how about the force? So if the limit or restrict only move along the surface, that means there's a force try to hold down, will not go inside, go below to the surface, right? So there's a force associated with the constraint. We call this the force or constraint force. That is a force due to constraint. Okay. Due to the constraint, they generate a force which can try to limit or restrict the motion of the object. So this particular force we introduce, or just classify the force, as I mentioned beginning, we can classify force in terms of external over internal or conservative, non-conservative. Now we're looking for the force such that it is due to the constraint. So we call those force a constraint force. Now if we introduce this, you will see this the feature of this. Okay. Can I use this one? Okay. So. Now, what is the feature of the constraint force? Can you express the force easily? We just know it's constrained on the curvature surface. How to write the force here at any position, right? If it is here, the constraint force is this way, right? And of course, this case you probably know, that is normal force. But this normal force change in any position, right? Orientation and magnitude. So it is not easy to express the constraint force. And now be expressed. That is a troublemaker because when we analyze using Newtonian mechanics, we need to analyze force first. We write down the force formula, then we set up, apply the second law. But if we cannot write force or express force expressly, how can we go further, right? So that is trouble here. Cannot be expressed straightforward. Okay. Immediately we cannot write down formula. That is hard or difficult. However, yes, we cannot write down or express the force itself, but we know what is the result due to this force, right? That is key, but we know, or we can know the effect of the constraint. Later we are going to discuss how to set up the effect, the constraint, different type of constraint, how to write this type of constraint or express. So that is the first issue, very important. Second one, okay, because difficulty, right? They are difficulty. So we are going to solve this Newton equation of motion. Then that's become the in solving equation of motion. Like Newton's second law. We need to analyze the net force or total force. But if the force includes the constraint force, it is very hard since we cannot express. So that makes the solving the equation of motion become very difficult. Almost finished the care of this third one. Two. No. Okay. It will reduce the number of degree freedom. Do you agree? Because we have to restrict, we have a limit or condition. Reduce the number of degrees of freedom. Very easily here, right? If this one is 3 degree freedom, we can move any, there is no restrict. But here, it is restricted in certain direction, so degree freedom reduced, right? Number of degree freedom reduced. That means if this is to determine how much, this is we are going to use very important degrees of freedom. Number of degree freedom is in, if we have n particles, each particle has an x, y, z, right? If a free here, we have 3 degree freedom for each particle. If the system includes n particles, each particle has a 3 degree freedom, so totally has 3n. This is no constraint, but we need to write minus k. So k is number of constraints. Okay, time is out here, right? So let's stop here and we keep continue on Thursday. When we deal with the constraint, first, how to write this, the second one here. How to express this constraint in terms of the effect. And then what type of constraint? We will have those type of constraint, so we are going to go further, consider how to solve this. If the system has a constraint, how to solve. All right.